Yeah, thanks, Bill, and good afternoon, everybody. It's early in the morning for me, but John gave me a call just to make sure that I'm here. And so we'll continue with the sessions of lectures that I've given. This one that I have for you today, to start today, is not in the same screen format as all the other ones. I simply didn't have time to get it to that larger landscape format, but it follows a similar principle in terms of the way I present the data. I try to explain things as I go along. And in this case, we start, so this is the type of things that I want to cover. That's also in the abstract. It's quite technical stuff, but I hope I can bring the message across with the examples that I've chosen to discuss. We start this conversation by looking at the thermal evolution of our planet. We all know that in the rock record, there's evidence of early accretion of planetesimals, and then the Earth heated up as a result of that, radiogenic heat production, which is what you can see on this dotted curve over here. And that radiogenic heat production has decayed with time, to the effect that the temperatures that we see in the mantle have, according to 3 different models that I've compiled over here, have peaked roughly about 3 billion years ago. That's why this big orange dot is over there. And since that time, the Earth has cooled down. And the way we see that expressed in the mantle is that the adiabat has actually changed. It used to be around 1500 degrees centigrade about 3 billion years ago. That's in the mid-Archean, and has cooled to 1330 degrees today. And it's a fairly linear path going from 3 billion years to today. And one of the ways we see that in the rock record is that komatiitic melts are very high magnesium. They require very high melting temperatures. And we know that they're restricted to the Archean rock record to a large degree. But this has also had a profound effect into the residues that have been produced as a result of melting in the mantle. And those are the residues that are today carried in the lithospheric roots. And so we see evidence of this process unfolding through geological age. And I'll show you the examples of that. That's the basis of a large proportion of this talk. So how does that work? If you take a standard piece of fertile mantle, the bulk composition of that fertile mantle will have about 48% olivine, 32% orthopyroxene, 18% clinopyroxene, and 2% spinel. It's a spinel hard lozolite, fertile lozolite. It's quite pyroxene rich and olivine poor when it's a fertile piece of mantle. In other words, it looks like a chondritic reservoir. And that plots over here in the standard rock classification diagram. If you start melting a fertile piece of mantle, I'm just going to turn my video off here. If you start melting this fertile piece of mantle, the first thing you will extract is clinopyroxene that sits over here. And so the residue will move away from clinopyroxene. It will move in this direction over here until you exhaust clinopyroxene at this line. And then you have to melt the next most meltable fraction of the rock, which is orthopyroxene. That sits over here. When you extract orthopyroxene from the rock, you drive the residue up towards olivine-rich compositions, and ultimately you create from a lozolite a rock that we call a harzbergite, and then ultimately from a harzbergite to a dunite. And so you make the rock olivine-rich as a result, and the residue then becomes what we call a depleted residue, or a residual fraction, a refractory rock type. The melts that you produce as a result of this process will live at the bottom of the triangle over here, They will be rich in clinopyroxene in particular, in the initial, but they will also start having orthopyroxene. These rocks are called pyroxenites. If you have them in the mantle, if they erupt at surface, we will call them basically tholeiitic basalts. So this is the process of how you extract basaltic melt out of peridotite and produce a depleted residue. And as I've said, the nature of that process has changed with time. This is another way of looking at that process from melting experiments that were done by Koshiro in Japan. And it just emphasizes the nature of the exhaustion of these different phases with increasing temperature and the residues that remain. So you will have a lersilytic residues up to about 20% melt extraction. From there onwards, a Harzbergitic residue up to about 40% melt extraction. And from there onwards, you'll have a dunite. Now, if we put Earth temperatures or adiabatic temperatures through time on the same diagram, and ultimately you'll melt olivine out, but that'll happen at very high temperatures. If you put those, the adiabatic temperatures through time on the same diagram, then you'll see that 3 billion years ago, so in the mid-Archean, the adiabat was hot enough to actually produce residues that are largely dunites. And then as the Earth has become aged, as it's aged and it's become younger in geological time, the capacity of the adiabat to produce dunites has decreased. By the time we get to the mid-Proterozoic, you can't produce dunite as a residue anymore. You can do Harzbergites. And today, you can hardly produce Harzbergite as a residue. Most of the residues we see today are lersilytic residues. And so in the roots of Archean cratons, which are this age over here, roughly 2.5 billion years ago, we expect to find evidence that there was melt extraction to the extent that you produced dunitic residues. In terms of whole rock chemistry, one of the major signals that we can see of this process, starting with a primitive mantle or an asthenosphere and extracting the melt out of it. It's an almost linear process in terms of calcium and also aluminium content, but there are other things that are going on in the background as well. The residual depleted mantle has higher magnesium over iron, so it's more magnesium. It has low aluminium, as we can see here. The aluminium gets extracted and therefore has higher chrome, so a higher chrome to aluminium ratio. Low calcium, also has low titanium. But this is a very useful vector. You can either measure calcium or aluminium in the bulk rock system, and you'll have a linear approximation of how much melt is. So why do we choose garnet to monitor all these processes? And it's the title for my talk. It's the perfect proxy for mantle rocks because it occurs in a very wide range of rock types. We've seen that, peridotite, pyroxenite, eclogite, and also megacrysts. Garnet has a wide pressure temperature stability field, including across graphite diamond, so that's important from our perspective. And we can also retrieve major element data and, as we've seen yesterday, temperature and pressure data at low unit cost. So it's a very useful proxy to have in the toolbox when you want to go and monitor stuff. In addition, the formula for a garnet, it has, beside the silica site and the oxygen site, it's a cubic mineral, but it has two sites that are largely independent of each other. On the X site, you find magnesium, iron, and calcium. And on the Y site, you find aluminium and chrome. And so you can monitor a whole range of different things in these two sites, and they reflect different attributes that you can extract from that garnet structure. So, for instance, the magnesium number reflects the olivine content, or the whole rock magnesium number. The calcium number on the X site reflects the presence of orthopyroxene and clinopyroxene. There's minor manganese and nickel. That's useful for mantle thermometry. On the Y side, you can monitor the chrome number. And that reflects the presence of chromite, or the whole rock chrome number. Ketani, you're quite loud in the background here. Can you switch off your mute, please? And then on the Y side, there's minor ferric ion content, which reflects the oxygen fugacity in the mantle. In addition, this is a very interesting aspect of garnet stoichiometry. You can measure the ratio of the Y to the X site, which is the ratio of chrome to calcium. And as I'll show you later, that's a barometer. So to have all these capacities encapsulated in one mineral, it's very useful from the single mineral approach. And you can monitor a variety of different things. And what I'll be showing you now is how it reflects the aging of our planet. So here's our standard chrome calcium diagram. If you go to an alkali basalt source where there's thin and hot lithosphere on the current in the present day, there will be no diamonds associated with that setting. You will find a fertile garnet composition in your garnet concentrate, which will be situated in this part of the diagram right here. That's where fertile mantle plots. And these data sets come from places like Paliaiki, the Antarctic, Vitim, Siberia, China, Mongolia. We've got lots of this kind of data set over here. Low chrome garnets with a reasonable amount of calcium in them. And the assemblage here will be olivine, orthopyroxene, clinopyroxene garnet. If you now extract a little bit of melt out of that fertile bulk composition, as was the case for the mantle underlying Gibeon, but there are also other places that you can find these kind of garnet patterns. The setting will be marginal kimberlites, sometimes we call them melnoites, thin lithospheres, mid-proterozoic, no diamonds associated. That's the kind of garnet pattern you see. And if you take that process even further, you extend this all the way up the lozolite trend over here. The setting will have kimberlites in it. The lithosphere can be quite thick. The age of the overlying craton will be late Archean, early Proterozoic. It's what I call a lozolite dominant mantle, all the way up the lozolite trend. Sometimes you find diamonds in there. They're often associated with the eclogitic fraction, which is down here on the diagram. This particular example is from Sloan Nicks. That's on the southern end of the Wyoming craton. But you can also find these kind of patterns in Finland, Prairie Creek, Mashgawan in India, Kundalungu in the central part of the DRC. So this range over here represents 5 to 20% melt extraction. Clinopyroxene is still present, it's not been exhausted, and therefore all the garnet compositions lie within the lozolite field. But if you take it a step further, you're now going to exhaust clinopyroxene and you get these kind of garnet patterns. You now step out of the clinopyroxene stable field and into this field over here. You start producing Hartsbergites as a residue. The settings are typically kimberlites, 200-kilometer lithosphere, typically Archean. You start seeing Hartsbergite being a significant component of the garnets that you recover in these settings. The diamonds are normally prototypic and also some eclogitic ones. This particular plot comes from Shandong in China. These are 550 million-year-old kimberlites. These are the garnet patterns that you see out of Shandong, but you can also find these kind of patterns in Botswana, Kuruman, and Bujimai in the DRC, in Mali, and then also on the southern slave. And it represents 5 to about 30% melt extraction. I've put a red line in here. It's a notional vertical red line. It's situated at, I just put it in at 1.8 weight% calcium. It could be at about 2. It could be about 1 weight% calcium. This is a notional line where you'll see orthopyroxene disappearing. And on the other side of this line would be dunites. So this is the Hartsbergite field over here. Once you exhaust orthopyroxene in the source, you'll be producing an olivine-rich rock. And that's what you see in settings like Siberia, where this data set comes from. It's from Aikal and Udit Schneier, and I've actually artificially added some eclogite at the bottom here. But you also see these kind of patterns in the Western Carbval, at Venetia, and the Central Slave Crater. So you associate them with kimberlites, thick lithospheres, early to mid-Archean settings. You see a strong Hartsbergitic signal, and then you start seeing dunite being present. The diamonds that are associated with these type of settings are prototypic and also eclogitic. And just notice over here at the top, we're talking here about OPX art at about 40% melting that drives your garnet compositions right down to these low calcium, very, very characteristic compositions of melt extraction under extremely high temperatures, which are typically Archean. So the process is then schematically illustrated by these yellow arrows. You can read about this. These diagrams, in fact, come from a paper that I published in '99 while I was still with De Beers, and most of these data sets were available to me as a function of the database that De Beers had available to us. There's a different way of looking at the same thing. So the chrome calcium plot has its uses in recognizing different residues that are sitting in the roots of the cratons. But you can also look at the magnesium number of the same of garnets to monitor the same process. Here I've used the garnet calcium intercept values that I explained yesterday as a monitor of whether you are in the leusolite field on the right or the Hartsbergite field on the left. And I've just plotted the phosphorite content of olivine that coexists with garnet as a monitor of the magnesium number. And this is based on mantle xenoliths from my database from Cr-pyrope and Lesotho. On this diagram, fertile mantle would plot over there. And if you do the same extraction process, you'll first extract cr-pyroxene until you exhaust cr-pyroxene. Then you'll cross the boundary into the Hartsbergite field and go all the way up to the dunite field over here, less than or about 1.8 weight, or 1.8 on the garnet calcium intercept number, and phosphorite contents that are around 95. So you start with a phosphorite content near 89, it's about 88.5. It goes up to about 93, and then all the way up to 95 over there. At the same time, you're exhausting titanium very quickly. Titanium partitions into the melt. And so the residue very rapidly has 0 titanium, and that's this yellow arrow over here. But there's something else going on this diagram over here. There's a whole lot of data that has much more titanium. And the reason for that is this depleted residue has experienced some metasomatism. Titanium has been added back into the system, and it's done so with characteristic slope like this. As you add titanium, you're also adding iron and calcium. And so this metasomatism has this very particular arrays that you see on these kind of diagrams. And Andy Moore will be very happy to see that megacrysts are represented. They basically are metasomatic additions to what is a fertile system to begin with. So megacrysts are evidence of refertilization of the mantle. And they play a particular role in defining what happens in the bottom end of this diagram over here. Okay, so I've armed you with some examples of how to interpret a chrome calcium diagram. Here's one that we can interpret right now. We can treat it as an unknown. I obviously know where this comes from. But if you were receiving this chrome calcium diagram, which is actually very well populated. There's 47,000 data points on this graph. And it's just an illustration of the nature of the data sets that are available to us these days. You can interpret this diagram in terms of the sources that are pushing out these garnets as xenocrysts. And in this case, you will choose a kimberlitic source because an alkali basalt source would be restricted to this bottom corner over here. You can interpret it in terms of the extent of depletion. In this case, you will argue it would have gone from 5% depletion all the way up to about 20% depletion, kleine pyroxene out into the Harzbergite field. And there are three different variants of that process represented on this diagram. There's a Harzbergite field that has been generated over here. There's another one that's been generated over there. And there's another one that's generated over here at very high chrome contents. Notice that all three of these do not pass materially beyond this boundary over here. So the proportion of dunite that you expect in this lithospheric residue is actually quite restricted, and it's not like the Carbval or Yakutia. The extent of depletion that we see on this particular data set did not go all the way to zero calcium in a garnet. It's a very subtle signal, but we'll see some differences in other chrome calcium plots that you'll see this morning, where you should look for what's going on in this part of the diagram over here, because it tells us the age of the mantle. You can simply look at your chrome calcium plot and say to yourself, I think this is an Archean mantle, but it's not as old in the Archean as we see elsewhere on our planet. And so maybe it's a mid-Archean mantle as opposed to an early Archean mantle. I don't know that there is much more that I could discuss in terms of lithospheric age, but we can already put some potential diamond associations on this plot. Obviously, there would be a paratitic diamond association, but there's also potential for an eclogitic diamond association sitting at the bottom of this diagram over there. And so all the information we need in terms of a regional assessment is available to us just simply by looking at this chrome calcium diagram. But wait, there's more. The diagram has a lot to offer. And some of you will have noticed that there are these sloping lines on this diagram. I pointed them out a bit earlier. So those are a function, and they're sloping in chrome and calcium content. Those are a function of the presence of chromite. And once that happens, you can squeeze some pressures out of the diagram. And those pressures then relate to the depth of which the depleted lithosphere extends to. I was fortunate enough to be able to, I did this work in about 1994, I think. And I was fortunate to be able to publish it. Thank you for De Beers for allowing me to do that. This is the diagram that came out as a result. These are minimum pressures calibrated against graphite diamond for assemblages that look like this, where you have chromite coexisting with a garnet, and it has either diamond in it, in a paratitic setting, either diamond in it, or in the case of the material down here, graphite in it. And these are very linear relationships. So I formulated the barometer simply in weight percent, because it's so easy to apply on this diagram, which is also stated in weight percent. Of course, the academics don't, they espouse this approach. They would much rather see this formulated in thermodynamic terms, but this is a very simple and effective way of conveying the barometric information that's available to us from this chrome calcium diagram. So somebody did ask the question yesterday in the chat, how do we know when a garnet coexists with a chromite? And the answer is, in general, you don't. So if we go backwards over here, you would never know that that garnet composition does or does not coexist with chromite. The only way that you will know that there is chromite coexistence ongoing in your data set is when you see these sloping arrays, like that one over there, or these ones over here. So let's go forward again. When you do have chromite coexisting with garnet, the pressure you get is a real pressure. If you don't know that, in other words, if you don't see those sloping arrays in your calcium plot, the pressure you have is a minimum pressure, and that is the general case. It's a very special case that you actually have the information available to you when garnet coexists with chromite. There's a little calibration detail which I'd like to share with you. When I did this work initially, I had a particular data set from the Cleve kimberlite that Bruce Wyatt investigated. He gave me this data set to look at, and it had this sloping line on it inside the leusolite field, but it's not a very well constrained line in the sense that, you know, there's no data down here on the line. And I used it with reservation. I've recently come across a paper that was published by some Russian scientists where they look at the lamprites from the Eldon Shield. This is the chrome calcium diagram that these guys have now published. There's 1,200 data points here. They've put out a data set with a line that goes all the way down here. And I'm pleased to report that their line is consistent with the sloping line that I fitted to the Cleve data set without any modification. So I'm very happy that these data sets are still coming out. There are additional bits and pieces that come out of this data set that's now being published. For instance, what are all these data points doing sitting on that line over there? And what's this single data point doing up here? There's some resolution that's happening in this part of the diagram that I am personally interested in, because there's some sloping lines that go upwards like that, which I believe are a result of spinel saturation in the rhyolite field, but that's a topic for another conversation. So we've come to the point in the talk where we can discuss two chrome calcium plots. We've already done this one with 47,000 data points on it. Here's another one that was published. It has 17,000 data points on it. So that's a full representation of the residue that's sitting in the lithospheric keel somewhere on our planet. And we now have a toolbox that we can assess what this chrome calcium plot is telling us. So first of all, how deep is this depleted lithosphere? This one over here, that garnet composition is telling you it's larger than 60 kilobars deep. That's quite deep. It's well into the diamond stability field on a normal geotherm. And if you don't believe that number, if you think that's a freak number, well, you can pick any one of these over there and you'll get numbers like 58 or 57 kilobars. So, you know, it's a mutually self-consistent plot. This is a deep lithosphere. It would extend into the diamond stability field on a normal geotherm. It hasn't had the depletion history that we often associate with Archean cratons. There's a lot of leusolite in the section. And there's a minor amount of harzbergite in the section, and there's no dunite. So this is potentially a proterozoic lithosphere. This might not be an Archean lithosphere. And it doesn't diminish the fact that you would still be associating diamonds with this part of the diagram and also with this part of the diagram down here. But the nature of the diamond mineralization and how that has come about will be different in terms of history from a lithosphere like this. And we'll see this diagram on the right-hand side again a little bit later this morning. The one on the left here, I cannot reveal. This is the chrome calcium plot that represents the root of the slave craton that Herb Helbstedt talked about 2 days ago in this course. And it has a structure where we have one set of depleted materials up to 61 kilobars. That's quite deep and it's spinel saturated, so we know it's a real pressure. And we don't see any evidence for depleted material deeper than that in the slave. This is a well-populated data set. This is the limit of where we're going to see these kind of pressures. There's another depleted layer that extends up to about 53 kilobars. That's again a real pressure. It's inside the diamond stability field, and it is responsible for a lot of the diamonds on the slave. A lot of the diamonds that you see on the slave are related to this layer of depleted lithosphere. There's another set of depleted lithosphere that goes in the range 38 to 42 kilobars. You could just see there's a density change in this diagram over here. This layer, actually, we know the thermometry of this layer. It sits in the graphite stability field underneath the slave. And there are very few diamonds associated with these kind of compositions in the slave. And that was a big surprise to the industry that we could get a lot of hard spaghetic material so shallow in the mantle section. And as we'll see later on, it's not unique to the slave. There's another setting where that has also occurred. Perhaps on this diagram, the sources for these kind of garnets are obviously kimberlites. They're not alkali basalts. Alkali basalts don't sample the mantle at these kind of pressures. The only melt that does that is a kimberlite. And I think there's time for some discussion or questions.
Just to kick off, Herman, where does all that data for the slave come from? Is that stuff from all the work being done there by the various companies and put on open file again? It's
open file. So in fact, the person who compiled all that data was John Armstrong, who is now with Lucara Diamonds. He's their diamond guy at Cr-pyrope.
Yeah.
He did all that work. I can remember the day when they released that open file. Everybody was just mobbing John Armstrong for the CD-ROM, and it was free.
And can you put it to sort of spatial context too? Remember Herb talked about sort of the west and the east.
Oh yeah.
I mean,
every data point that's on that graph has a sample position associated with it.
Okay. So if you go back to that diagram, where would the western side would be presumably then more in the graphite area, where Herb said there were no diametriferous pipes.
So yeah, I should have actually put a map up here. Normally I would.
They'll let you off this time.
Yeah. This signal that we see over here, this very depleted shallow signal, is in the central part of the slave.
Okay.
It's underlying. So if you drill down at Diavik and Ikari, that's where all this data comes from.
Okay. So it's mostly.
If you go to the northern slave, it's completely absent.
Okay.
And if you go to the southern slave, it's also completely absent. It's sandwiched. It's a very particular feature, sandwiched in the middle of the slave craton.
Yeah, it was that long belt that he showed us, sort of, with fault bounded on either side, structurally bounded. Yeah. Okay, and at a guesstimate, I mean, where would the carp valve sort of Kimberley block sit again? Would you see a similar profile? I mean, you've looked at enough data.
Look, unfortunately, we don't have the open file data for the carp valve.
Yeah.
The closest I can get to, there is a data set that Dion de Bruin put together for the CGS, for the Council for Geoscience in South Africa, from alluvials. So that was a sampling of the Western carp valve, alluvials.
Okay. Yeah.
And it looks it looks kind of similar, but it doesn't have this layered structure that you have in the sort of definite layered structure that you have in the slave craton. I think that was a big surprise to everybody, that ultimately when we compiled all the bits and pieces across the whole slave craton, there was so much diversity in the lithospheric section in the slave craton. If you condition yourself with a Cr-pyrope craton, you don't expect to see these kind of relationships elsewhere. I think perhaps if we can go back here, this is a data set for Aikal and Udjnaya.
That was going to be my next question. What about Russia?
Yeah, so this is basically, this is Russia. This is what I forget the name of the name of the craton, the Russian craton, but it's the Yakutian craton. That's what it looks like. The Cr-pyrope is not dissimilar.
Okay.
And that's what I say here. The other examples of this kind of pattern is the Western Cr-pyrope, Venetia, and the central portion of the slate.
Interesting. So effectively, I mean, you end up developing sort of macro tools to, better understand the cratonic setting as well.
Yeah, I mean, it's a diagram. It's remarkable, right? That garnet happens to be stable across this whole pressure range inside cratonic roots, and you can record all of these attributes simply by looking at a chrome calcium diagram.
And then just getting back to the question yesterday on the garnets, or the really refractory stuff.
Well, there you go. There they are.
Yeah.
And who are the people that have described garnet xenoliths, and from which locality? The Russians described garnet xenoliths, some of them with diamonds in them, from Udjnaya. There's the evidence that they should exist. And if you look at the garnet compositions from those garnet xenoliths, they're down here.
Yeah, very refractory, very chrome rich, very low calcium.
And just to take that point a little bit further, the phosphorite content of the garnet xenoliths is FO95. FO94 to FO95. That's these kind of compositions.
Interesting. So where are the next cratons that we should be looking at, or these are really unique cratons?
I've developed a view, just to answer that question very shortly. I've developed a view that every craton is unique.
Every craton is different.
Every craton is different.
Yeah,
they have generic features that are shared, but the nature of how they've been compiled and assembled through time and how they represent to us today, each one has a unique history.
No, that fits perfectly. So I mean, you go back to Clifford's rule, as a sort of broad rule of thumb at that point in time, with the knowledge that was available. And when was that? Back in the 70s. It was a very useful tool. But credit to you and others and the Russians and so on. I mean, this process has moved on with leaps and bounds.
Tom Clifford was papers 1966.
Okay, thanks, Paul.
And it's really interesting for younger kids around here that, that took at least 15 years for general acceptance when you think about it. Plate tectonics was in its infancy at that time. And it took many years before that was accepted as well.
Yeah.
Far different pace of acceptance of new ideas today than there was in those days, I think.
But again, Herman, I mean, thanks for your insight, and I guess what you've shown is the importance of big data.
Well, yes, and remember that when I published this paper in 1999, I had access to the big data that De Beers had.
Yeah.
So the power of big data is enduring. And credit to De Beers for allowing me to put these kind of concepts into a publication.
Yeah. Yeah, but I mean, again, credit to you that, you've continued to build these data sets, and your other colleagues, in Canada, and John Armstrong, and, you can now look at it from further evolution of the process.
Yeah, so I think the whole Canadian setup has changed the nature of the industry, and in large part as a result of the fact that people have to publish their microdiamond results. People have to file assessment reports. Those assessment reports become public domain information, and people are hungry for knowledge.
Yeah. No, I think absolutely. I mean, love it or not. I mean, the Canadian approach to transparency, and I guess that's that's one of the upsides of having lots of juniors who need to move their share price. So every time you found a diamond or a micro diamond, you announced it. But it does have its benefits as well.
It's a functionality of a vibrant junior sector, John. I think that's a very fair point to make.
Mm-hmm. How do the fragments of megacrystic garnets feature in the various garnet plots?
Okay. Hi, Jürgen. You're back again with a good question. So megacrysts actually plot slightly over here. They're slightly higher calcium than the depleted mantle material. They represent a more fertile composition, and they're an addition to depleted mantle. So they don't belong inside the depleted mantle spectrum. And so much of the talks that I have not spoken about megacrysts to a significant degree, because they represent, if you think about it, a metasomatic addition, and it's a fertile metasomatic addition. I did point them out on this diagram over here, and you can see that, this is fertile mantle. It doesn't exist, and it's an open box. It doesn't exist in cratonic roots. Everything that we have in cratonic roots has been depleted to some degree. That's the depletion vector. But then there's been an addition, and one of the additions is megacrysts. They point backwards to a fertile assemblage that has been added basically to the base of the lithosphere. I hope that answers your question.
That's very useful. And Andy, I notice you're very quiet. Are you still in shock having seen that picture of yourself back in your 20s, was it?
No, it's fine, John. I've just poured a beer. I've made a massive recovery.
Good.
No, I was just going to say that one of the things that would be worth looking at is the Zimbabwe data. Chris Smith published stuff in the 9th Kimberlite conference, and you get very, very refractory chromites and garnets from Zimbabwe, and you look at them and you think you've hit the jackpot, and it's, they just don't support the grades you expect. Moreau is obviously an exception, and if you get south into Venetia, well, you're in the Limpopo belt. But they commented that the Greenland kimberlites were similar. I haven't seen that data. I know Herman's worked there. Have you got a comment on the Greenland lithosphere, Herman?
Yeah, next talk.
Oh, okay. Just one other thing, just to have a dissident, the megacryst event is probably, if you believe Mercier, going back to the second conference, not something that's happening at the base of the lithosphere, but around the kimberlite magma before eruption. And he said in a narrow zone, maybe 15 to 50 meters wide. So that's not a sort of an extensive metasomatism. It's a restricted one, but I think that might be regarded as a minority view of perhaps one.
Yeah, I'm not going to launch into a conversation with you about megacrysts in this forum. We could do that separately. But I agree. I mean, they are very restricted. You don't find megacrysts everywhere. And it's a very simple observation. You know, we focus on the megacryst switch in particular localities where it's well developed. So it's not a universal feature. It's a localized feature.